Right. So, just because we don't know where everything is yet, homework, this week's homework is due here in the same place you've been, hopefully doing it. And Anupam will hold his office hours here today, at the usual time. As I had sent, I hope you received the email that we don't have a colloquium this week. So that's a slot that's available for everybody. So we'll have our class. I'll have the honor of teaching the very last class that will ever be taught in this building. You will be part of history. We will turn the lights off as we leave. It's like, I don't know, you had the two young, remember the Mary Tyler Moore show? It was a famous show from the 1970s. And, Mary closed the lights on the news set and everything. The show was very sad, but it was a closure for the show. So we're going to get to do that closure. Manuel has uploaded all of the videos onto YouTube, including the previous ones. So until we get our new server up and running, you can access those if you want to review any of the materials. Okay? All right. Very good. All right. So last time we began our foray into talking about quantum field theory, as we are about to talk really about the heart of what we will call quantum optics, which is the quantum aspect of the field itself, the electromagnetic field. So we're just setting some groundwork here and notation and some basic concepts. So when thinking about a field, as we will elaborate more through this lecture, we think about the field as having a collection of degrees of freedom, and those degrees of freedom we can think about as the normal modes of oscillation. Okay? So normal modes, the dynamics of normal modes are the dynamics of harmonic oscillators. So to think about a quantum field, we need to basically understand the simple harmonic oscillator. And people famously say quantum optics is the story of two-level atoms and harmonic oscillators, and that's basically it. You can get a lot of mileage out of that. I mean, today's a three-level atom, but it's a little bit of an aside. Right. So just to establish some notation and conventions, we look at a simple harmonic oscillator, just classical description, the Hamiltonian, written this way, defined by two parameters, the mass and the oscillation frequency, and from those we can relate the various scales to one another. Okay? So if there's some characteristic energy scale, we would naturally define a characteristic, a length scale and momentum scale that connects them. Okay? Now, there are the dreaded factors of two. And, one of these days I'm going to have to be less lazy and fix the notes, because there's a different convention in the notes than the one I'm using right now. And I will try to fix that soon. Okay? But really the question of, there is this factor of two here, and the question is, where do you put it? It's really natural to not include it in the scales, although it makes there are other than factors of two that get dragged around here and there. Okay? So, with that said, the Hamiltonian then takes this nice form, once we've defined these scales, which is symmetric in positional momentum, which is what makes the harmonic oscillator so nice, is that it is the same in X and P. we defined, importantly, in thinking about the harmonic oscillator, any harmonic motion, we should define a complex amplitude that relates the complex amplitude of the phasor in competent space to two quadratures, as we call them, x and p. So x is the real part of alpha times square root of 2, and p is the imaginary part of alpha times square root of 2. I mean, it's that stupid 2 that you have to put somewhere. The phase space that describes the trajectory of this particle as a harmonic oscillator, the free harmonic motion, is then just the circular motion of the phase space, which represents the rotation of this phasor clockwise with frequency omega, which is why the right convention is e to the minus I omega t. That's why it's e to the minus I omega t, because the phase relative to this axis is subtracted. You subtract off the minus I omega t. That's why engineers have it wrong. It's not, if you want to be an engineer, you might minus I is plus j. Anyway. All right. Very good. And of course, the energy of the system is related to the square of the amplitude, okay? So that the energy is alpha squared in units of whatever the characteristic energy scale we defined here is. So you tell me the energy, that's all you need to know, of course, when you have a system with 1 degree of freedom in a Hamiltonian system, you tell me the energy, that's basically the story, plus the initial conditions. Okay. All right, this notation and these relationships are extremely important. And they're basically, you know, we're going to be talking about this for months to come in different ways. All right, so, of course now, given this, we can quickly write down the quantum. That. Simple harmonic oscillator. So, firstly, when we talk about quantizing the oscillator, well, we have one new characteristic scale in the problem, which is h bar, right? So now, in addition to the mass and the frequency, we have h bar. And so, given that, we can define all of the scales of the problem. So given these quantities, h bar, the mass, and the frequency, what is the natural energy scale of the problem? H bar omega, right? That's how you make a frequency, an energy out of these quantities. And then that thus defines the characteristic length scale, given here, plugging that in, and the characteristic momentum scale. Right? Just plugging that in. Of course, if I look at that, I can see that the product of the characteristic length scale times the characteristic momentum scale is equal to h bar, which is the characteristic unit of action. Right? So that's all makes lots of good sense. All right, so to quantize, we now, our canonical coordinates now have our canonical commutation relations. and thus expressed in terms of the dimensionless variables. This is I. Okay, so I'm defining our dimensionless position operator and dimensionless momentum operator in terms of, get myself more than midget chalk. I'm defining the dimensionless position momentum operators in terms of the characteristic scales. Okay. And the H bar goes away. In addition, we can define a non-Hermitian operator as the quantized version of the complex amplitude. And we define that as A. So that's the quantized version of the complex amplitude. Right? Now the Hamiltonian of the system is h bar omega x squared plus p squared. This was what we had. This was the characteristic energy scale. X squared plus p squared over 2, as we had before. Okay? And now if I plug in x is equal to a plus a dagger over root 2, and p is the anti-Hermitian part, times root 2, just like we had over there, but now with a's and a daggers rather than alphas and alpha stars, and plug that in over here, I get this is equal to now importantly, as you know, A does not commute with a dagger. Okay, so I have to be careful whenever writing A and a dagger to not just commute them as I would numbers like alpha and alpha star. I have to be careful about that. And of course, A with a dagger, plugging in this and this, gives A with a dagger is equal to 1. Okay, yep.
I forgot how that order came about.
This, I just plugged in, I didn't do all the algebra. I took this, plugged it in here and squared it. Take this, plug it in here, square it, and write out all the terms. And so I am not assuming anything order. So I'll have, for example, x squared is equal to a plus a dagger squared over 2. Right, that's x squared, which is a squared plus a dagger squared plus a times a dagger plus a dagger times a. Just multiplying, just put it next to itself and multiply it out over 2. And similarly for p. If I do that for p squared, what I'm going to get in this case is the guys with the i's are going to have, this is going to have a minus sign. And then that's going to be the same. And then I put that all in, and I get that. So that's what I'm doing. Is that clear?
So you don't, so you don't have to go and make some statements about the alpha.
You don't. I'm just plugging in for x and p in terms of a and a dagger and multiplying it out and not assuming they commute. If I because they don't. And therefore I get this. Okay. So now, of course, if I want to write this in the other order, I have to add the commutator, right? So that adds 1 to that. So that gives me twice this plus 1, or h bar of omega times a dagger a plus a half. Isn't that fun? So that a half, of course, differs from the naive quantization here. I mean, if I wanted to, it would be more natural in this case to just write this in the symmetric order. This is kind of a fudge, as I think Dave, you referred to. I could do that and say, oh, look, now I'm just going to quantize that. And that's a natural thing to do because this doesn't favor a alpha over alpha star. You got to love all your children equally, and alpha star. They're children. They're siblings. So you can't put one in front of the other. You have to get, they say, everyone gets a fair share. All right. Right. Okay, so to continue this review, this operator is the number operator. This is a Hermitian operator. All right, so of course we know that the eigenvalues of that operator are the non-negative integers, the numbers. So of course we know that, just to remind you quickly, the commutator, that's very quick to show that this is true. And the number operator has eigenvalues that start at 0 and are the integers of infinity. Okay. It's an infinite dimensional Hilbert space, of course. And the set, these states are known as Fock states. Really, or number states. And of course, they are also the energy eigenstates because the Hamiltonian is just a scaled version of the number operator with a constant. So the energy eigenvalues are n plus a half h bar omega. And so, when we think about this as a particle in a parabolic well, we have this harmonic ladder with equal spacing h bar omega between each energy level. The lowest energy level, the ground state, has n equals 0. The first excited state has n equals 1, etc. Right. Of course, based on these relationships, we know that very interestingly, what was the complex amplitude in the classical simple harmonic oscillator now has a new role in life in quantum mechanics as the ladder operators acting as raising and lowering operators. So if I take this operator A and I operate on one of the Fock states, I get I lower it, so this is the raising operator, the lowering operator, and then I have the raising operator, a dagger, that does this. And of course, this is not a, this constant here is because this is not a unitary operator, it changes the length of this thing. Okay? And of course, the ground state is annihilated by the lowering operator. Excuse me, the null integer. From this, it also means that I can get to the nth energy level by just applying the raising operator n times to the ground state and then appropriately normalizing it. All relationships you all know inside and out, I'm sure. If not, time to make sure your insides are with your outsides and get with this, all right? Very good. Of course, importantly, these states are not eigenstates of position nor momentum, right? They are eigenstates of the Hamiltonian. The Hamiltonian doesn't commute with position nor does it commute with momentum. If I look at the expected value of position or the expected value of momentum in any of these states, because of parity, that's zero. They're parity eigenstates. If I look at the parity operator on these guys, I get -1 to the n. So this is the parity which switches x to -x and p to -p, and these are parity eigenstates. So of course we know them as the wave functions in position space are the Hermite Gaussians, right? And the mean position, the expected value. However, the fluctuations are non-zero. So if I look at the fluctuations in the ground state, say, of x squared, so delta x squared is equal to this minus the mean value squared, but the mean value is 0. And so what is this, and how do you do that? If I don't remember what the number is, how do I calculate that expectation value quickly? Yeah, use the ladder operators. I mean, I could, if I was really a masochist, use Hermite Gaussians and think about Gaussian integrals, and maybe the God who would do that. So you write this as x squared, but x somewhere here is a plus a dagger over root 2 squared. So this is a half a plus a dagger squared, right? Now how do you calculate that? Well, what you do is you notice that when A hits the ground state, it annihilates it. And if a dagger hits the bra, it also annihilates it, right? Because that's the conjugate term to this. So the only term that survives in here are the terms that are what we call anti-normally ordered. We'll talk about normal and anti-normally ordered soon enough, but normal orders, you have all the A daggers to the left and all the A's to the right. Anti-normal order is the other. The only surviving term is one where I have an A dagger on the right and an A on the left. That's the only. Otherwise, I'll hit an A on the ket or an A dagger on the bra, and poof, that term is gone. Right? So this is equal to what? This expectation value. 1. I see that because I just now write this as 1 plus the commutator. I look at it, this is equal to a dagger A plus the commutator. Right, and this, poof, and then I get a half. And similarly for momentum squared is also that. So, as you know, the ground state of the harmonic oscillator is a minimum uncertainty state satisfying, right? Each one of these is 1 over square root of 2. You multiply them together, they have this minimum search. So often when we think about this, if I want to think about the quantum simple harmonic oscillator, I can draw a kind of equivalent phase space diagram to the one that we did classically, but with some caveats. So I have my phase space that we had classically normalized that way, where the lowest energy state would be what classically?
0.
0. Just sitting there with no position, you know, at equilibrium at x equals 0 with no motion, right? But quantumly, we can't be at a point in phase space. That violates the uncertainty principle. So we think that there's a little quantum fuzzball here with uncertainty, quantum uncertainty, that says something like the full width half maximum or something like that is 1 over root 2 along P and 1 over root 2 along X. Okay. So the ground state of the quantum simple harmonic oscillator has what we call quantum fluctuations. There's uncertainty. If I were to prepare in the ground state and measure the position or the momentum, I wouldn't get a definite value. We know we get the Gaussian distribution because that's the wave function for position and momentum. And this is a kind of joint probability distribution in position and momentum. Can we do that? Can we write down a joint probability distribution in position and momentum? That seems like quantum mechanics is just classical statistical physics. And the answer is sometimes we can, and sometimes it's just classical. There's no difference between the quantum mechanics and the classical statistical physics. And when it does differ, so that's in some sense one of the ways we're going to be able to distinguish between what we call classical light versus non-classical light. Can we think about it as just a classical random phasor of the kind you studied in your early homework? You're like, why did you give us those homework assignments? It has nothing to do with what we're talking about in class. Well, we're getting there. Okay. Turns out the ground state is kind of classical. It's just a Gaussian, joint Gaussian distribution, as we will see in a more formal sense. Those of you who took 491 or 2 with me, we can study the bigger function. What about the first excited state? Well, the first excited state, has some energy out there, h bar omega away from that. Classically, it would be some circle with a radius h bar omega plus a half away from the ground state. But quantumly, can I just think about, maybe there's some fuzz around this that says that x and t. Is that? Maybe. Maybe not. We'll get to that. Think about it. In what way is the first excited state classical or not? To be continued. All right. So, there's some important lessons to take away from what we've been discussing just this morning is, when thinking about the harmonic oscillator, we have this classical picture in terms of phasors with complex amplitudes and a phase space associated with that motion. Quantumly, we have this notion of energy levels, Fock states, and we will ultimately want to be understanding the interrelationship between those things. Okay. All right. Very good. All right, so this was about one mass on a spring. Now we want to talk about quantum fields. So we'll start with the simplest possible problem. We'll talk about a so-called scalar field. For elastic vibrations on a rod. Okay? So, well, think about a rod where we can have longitudinal waves at some position along here. There's some displacement away from equilibrium. And that displacement we'll call eta at this position in space, as it makes it a field as a function of time. Okay? So these are we'll think about longitudinal waves, just for simplicity. Okay? So like I would take the hammer and something propagates down the rod. Okay? This rod has a mass density mu, I'll call it. It's the mass per unit length. And it has something which tells me something about the elasticity of that, which in continuum mechanics that no one ever learns, including me. And I'm that old, but I still never learned this stuff really. Something called the Young's modulus. You guys ever heard of the Young's modulus? Right? This is kind of the spring constant times length. Okay, so what we want to think about now is thinking about the field theory. We want to write down a canonical theory with a Hamiltonian that describes the dynamics of this field. So to do that, what we're going to do is we're going to go to the continuum limit, starting from the limit of a bunch of coupled masses on springs, because we know how to write down the Hamiltonian or Lagrangian for the masses on the springs. Yeah?
And if eta of x moves, then eta of x is no longer at x.
I'm saying at this position, this is what this little mass is displaced from equilibrium. If you like, more easily to think about, let's think about a transverse wave.
Yeah.
So I'm displacing it from there. This is saying there are some, masses on springs, and they are displaced at this position. The matter doesn't move. It's the excitation that propagates through, just like any wave, the longitudinal wave. Like think about a sound wave. In a pressure, the molecules bounce off one another, and I can ask what is the displacement of that pressure of that gas away from equilibrium.
Okay.
Right. So we're going to go to the continuum limit. Of masses on springs. So we'll imagine a chain of masses. I'm not going to say anything yet about the boundary conditions. and they're connected by springs. So each mass is equivalent, has mass m, and there's a spring constant. Okay. So there's the ith mass here, which is at position x of I, and this is the one at position x of I plus 1. And each one of these, the displacement away from its equilibrium value is x of I sub 1. And so this guy, there's an equilibrium value that's now displaced to that value, and that amount of displacement, the amount by which this mass is displaced, the ith mass is displaced from equilibrium, I'm calling x of I. All right? And similarly, this guy gets displaced by some amount x of I plus 1, the I plus 1 mass. Okay? So, now I can write down the Lagrangian. The kinetic energy of the system is the sum of the kinetic energies of each of the masses. And the potential energy is the stretching, the relative coordinate stretch, the difference between I and I plus 1 squared gives me that much compression or stretching of that spring. Okay? So that's the potential energy, and the Lagrangian is T minus V. Okay? All right, so now I'm going to go to the continuum limit. Okay? So if these masses at equilibrium are spaced by some amount A, what I'm going to do is I'm going to take the limit as A goes to 0 here as a differential, so that I can think about this as a continuum rod rather than a discrete set of point masses. Okay? So I'm going to take the limit as A goes to a differential, and the total mass of the system, so M over A will go to the mass density, and the kappa times A will go to the Young's modulus. Okay. Right, so let's now what is going on over here? This is where it gets a little bit tricky. What was I now? This is ith position, ith plus 1 position, ith plus 2 position. Now becomes the continuum position on the rod, and the amount of displacement at the ith position becomes eta. Right? So in the continuum limit, x of I goes to eta at x. I goes to this. The amount of displacement goes to eta. Is that clear? All right, good. So now in this, let's just rewrite this. Sum over I, I'm just going to first just rewrite T this way. I haven't done anything except multiply and divide by A. Now I'm going to take the limit, as we just said here, and the sum now becomes an integral dx. That's this part. This becomes a half the mass density, and now I have the partial derivative of eta with respect to time squared. Okay. So this was a function of time, and so is this.
So what happened with factor of A?
This becomes dx.
Okay.
Similarly, I'm gonna multiply and divide by a squared. So I'm gonna get a half kappa a xi plus 1 minus xi over a squared. So I multiply by a squared and divide by a squared. And now I take this limit. And once again, the sum becomes an integral dx. This is a half times the Young's modulus. And this is now the partial derivative of eta with respect to x. And so the Lagrangian for the field, now the field represents this. This is the field. And so the Lagrangian now takes the form, the integral dx, a half the mass density d eta dt squared minus a half the Young's modulus d eta dx squared. Yes, sir.
The A is, you could pick A or A over 2. My question is, KA, I don't know enough about.
Me neither, and I don't want to get stuck on it. It's really not important. Believe me, read in Goldstein about the way in which Young's modulus are related to kappa. This is just the continuum limit of breaking this up into a bunch of differentials and thinking about mass springs. I don't want to get stuck on the continuum mechanics because honestly, Dave, I don't know the answer. So I leave it to you to read that. It's not the important thing to focus on. Let's focus on the important things, not the unimportant things. Okay? All right, so given this, by the way, this object is what's known as the Lagrangian density. It's the Lagrangian per unit length on this graph. Okay. Now, when thinking about fields in the continuum, we have a generalization of the Euler-Lagrange equations, the ones that we wrote down last time for thinking about discrete degrees of freedom. When you have a continuum in space and time, we have a generalization. So now, the Euler-Lagrange equations which tells me the equation of motion for how the field dynamically evolves, has a following form. I do the partial with respect to time, and then the so-called functional derivative with respect to eta dot. This would be the kind of thing you would have for a Q, right? If I could think about this as a canonical, or as a canonical coordinate, there would be the derivative with respect to time of the partial Lagrangian with respect to Q dot. But in this, when you have a field, space and time are kind of the same thing. So I have to add to this the partial with respect to x of the functional derivative with respect to that. That's a new term that arises. And if I had it in multiple dimensions, I would have the dx, dy, all of those things. And then that is equal to minus L d. So that's the generalization of the Euler-Lagrange equations when I have fields. This thing is known as the functional derivative. So I'm making a derivative with respect to a function. It's a very formal object, but basically we can treat it the same way as we treat any partial derivative. And if I look at the partial derivative of the Lagrange density with respect to this variable, this thing is equal to mu d eta dt. And this thing is minus y d eta dx. And there is no dependence on eta alone, so that left right-hand side is 0. And so the equation of motion for the field is the following. d eta dt squared minus y over mu d eta dx squared is equal to 0. And that is what?
Wave equation.
That's a wave equation in 1D. So the equation of motion for the field is what we expect it to be. There are waves that propagate along this elastic rod. What is the phase velocity of those waves?
U by unit squared.
I'm listening. Square root of y over mu, right? Because the general form of the wave equation for an arbitrary wave, some wave psi, is that, right? Okay, very good. Now, we can quantize this in terms of the fields themselves, but it is much more convenient to think of the appropriate degrees of freedom as a discrete set, once again. So once we've gone to the continuum limit, it seems like we've lost the discrete set. Now, what's discrete? We can make it a discrete set if we put on boundary conditions. So, let's think about the normal modes of the system. So, we write the normal modes, we do the separation of variable, where we have some time dependence and some distance dependence. We look for solutions of that form and do the usual separation of variables. So when I plug that into this equation, so now let's see, I have my equation of motion here. I'm going to write it in the following way. We have like this. I plug in these this separable ansatz, and I get the usual thing, separation constant. And this has to be equal to some constant, which, if we want this to have the right behavior and not blow up, has to be a negative times a positive number, which we'll call k squared. So that's the usual separation of variables, right? So this guy has to have a, where did I got this? The 1 over b squared. Right. So with that said, we have that k, I'll write this, I'm sorry, the spatial part of this, for that separation constant, satisfies this equation, and this guy satisfies this equation, where omega sub k is v times k. So, for a normal mode, the temporal part is a simple harmonic oscillator with frequency omega sub k. So that's what makes a normal mode, in that the temporal evolution is just simple harmonic motion in time. Okay? The spatial solution depends on the boundary conditions. This is a function of x. So, if we think about hard wall boundary conditions, so I have, say, a wall at x equals 0 and a wall at x equals L, where that's the length of the rod. My rod is pinned in between these things. Then it can't displace on that. We have the boundary condition that eta has to be 0 at each end. The solution to this differential equation, which satisfies those hard wall boundary conditions, then is equal to something which is proportional to sine kx, where k at L has to be some multiple of pi. Right? So really, I should write these as k sub j, labeled by that, but typically we just sum over k, knowing that the k's are equal to some multiple of pi over L. Okay? So those are normal modes, and we like to normalize them, square normalizable, over the rod, so that this is 1, and that puts a normalization like that. If I had periodic boundary conditions, which would correspond to a ring, so So now this is the picture of thinking about my elastic rod as a ring, where x now is the distance along the circumference. So that u sub k at x has to be periodic. Then the solution in this case is, here J, by the way, is an integer, 1, 2, 3, etc. The lowest state being a half wave inside the boundary conditions. In this case, UK of x normalized that way is 1 over square root of L e to the I k x. So they're like propagating waves. They can propagate either one direction or the other. K in this case, to be periodic, is this, where now J is plus or minus 1, plus or minus 2, plus or minus 3, etc. So, these sets of normal modes form a complete set of orthonormal functions over the rod from 0 to L, okay? So I can decompose any spatial distribution initially into some number of normal modes. These are a complete set over that interval, right? That is to say, if I sum over all the modes, for either of these cases, now I'd have to put a star in the case of this guy, that is a delta function. And that's a statement of completeness of modes. It's like, inserting the complete set in quantum mechanics. Right. Okay, so with that said, because they are complete, what it says is that I can always write any field, I can decompose it into the normal modes. At any initial time, there is some coefficients that tell me how much of each of the normal modes are, and that coefficient will evolve in time. Now, so this is a general decomposition of this field in terms of normal modes, because these are a complete set. Okay, is that clear? Now, we want to, just for convenience, it's nice to have this thing have the same units as this, which was length. Okay, and this thing has some weird units over here. So I'm going to factor out a square root of L, because this thing has units. And then I'll call this Q. Okay, I'm just factoring it out. So now this thing has units of length. It has the same units as this. Eta was how much the length would tell me how much I was displaced along the rod. Okay, let's take this ansatz, which is a decomposition of the field in terms of normal modes, and plug it into our Lagrangian. Okay. So our Lagrangian was that. I'm going to take my decomposition in terms of normal modes and plug that in over here. Okay. So when I do that, let's look at one of these terms. Let's look at this guy. Let's look at the kinetic energy term. That kinetic energy term, let's see, I'm going to plug that in. I get an L, I get the sum over two things, K and K prime. I'm going to get the mu over 2 out front. I'm going to get the partial respect to time gives me a time derivative on this guy and that guy, and then I'm going to get an integral dx u of x u prime of x. Right? And what is this? I didn't actually say that. But what is that? That's a delta function, because not only these are complete, they're orthogonal. That is, if I look at the normal modes for two different values of the mode index, I get the Kronecker delta. So this is a Kronecker delta. And this is the total mass. And so I sum over that delta, I get 1/2 the total mass, that's this guy, times Q dot squared. That's the kinetic energy. The kinetic energy of this field is the sum of the kinetic energies of all the normal modes. Each normal mode has a normal mode coordinate. There's a lot of abstraction here, but you should have learned this someday in classical mechanics. The amount of normal mode is the coordinate, the canonical coordinate of that normal mode. So this coefficient, which told me how much of that normal mode, is like the coordinate, the canonical coordinate of that normal mode. This is not the position of one of the points in that, we had another position, which was there was a mass on a spring, which had a position. That's not what this is. This is an abstract coordinate. It tells me how much of that normal mode I have, which evolves according to the simple harmonic oscillator. And it has that much kinetic energy. What about the potential energy? Well, the potential energy of the system, let's write that out. I'm going to get the Young's modulus, whatever the hell that is, over 2. I got the sum over k prime. I have the integral dx. Well, I have actually q of k and q of k prime. And then I'm going to get the integral dx, the partial of u let's see what I'm going to do here, are you? When I plug in the sum, right? I'm going to get this times itself, and I have two different sums, a sum over k and a sum over k prime. Okay. Any suggestions of how to deal with this?
Integration by parts.
Integration by parts, my favorite thing to do when you see a derivative in an integral. And so the way you integrate by parts is you take the derivative of one term and you put it onto the other term and you put a minus sign in front of it. And then you ask about the surface terms, the things that evaluate at the endpoints. But the difference at the endpoints is zero. Either it's periodic or it's zero at the endpoint. So the surface terms don't contribute to the integration by parts. So, minus. And this is, of course, a full derivative because this thing only depends on one coordinate, x. And what is that equal to? There it is. It equals to minus k squared times that, right? So, with a swipe of the eraser, I get k squared over there, right? There was an L, the total length of this thing, right? Somewhere. It was out here when I took the square and I forgot to put it in. This is a delta function. Right? So, let's see, we have a few different relationships here. I don't know if they've remained. We have a relationship between omega and k and v, right? V is equal to so if I write this out, this relationship here says that k squared is equal to omega sub k squared over v squared. That's a familiar relationship, the relationship between k, omega, and v, right? So I'm going to write k squared over there as, that shouldn't have come outside the integral, shouldn't it? It should have stayed inside. But some can't come out. So let's write that out. That's equal to L y over 2. The sum k squared is equal to omega sub k squared over v squared. Q sub k squared. Right? But what is v squared? V squared was equal to y over mu, right? In the phase velocity. So 1 over v squared is mu over y. So when you put it all together and you get the sum over k, 1/2 mu times L, which is the mass, omega sub k squared, Q sub k squared. Voila. So, what we have found is that the kinetic energy is the sum of the kinetic energies of a bunch of harmonic oscillators, and the potential energy is the potential energy of a bunch of harmonic oscillators. And so we have written this system in terms of, by writing in terms of normal modes, the Lagrangian is just the Lagrangian for a set of harmonic oscillators. We've gone from continuum to discrete by writing this in terms of normal modes with boundary conditions. Sum over modes we're kind of back to where we started. But now, the discrete set of variables is not the point masses that made up the masses on the springs, but the normal mode coordinates. Okay? And I can define a conjugate momentum just from the Euler-Lagrange equations, just as before. And write down a Hamiltonian for my field as the Hamiltonian associated with a bunch of harmonic oscillators. But those harmonic oscillators are the harmonic oscillators for the modes. And I can think about this as I like, just as before. I have some characteristic energy for each harmonic oscillator and define dimensionless coordinates, just as I did before, but now for each normal mode, or in terms of the complex amplitudes, where these represent the complex amplitude for each So, with the wave of the chalk, I can now write down the quantum field. The quantum field is just I've now quantized the field. Each harmonic oscillator that describes a normal mode of vibration is a quantum simple harmonic oscillator. Okay. And I can define the ladder operators for those in the same way. So my Hamiltonian now is equal to the sum over the modes, whatever the h bar omega sub k, x squared and p squared for that mode. Those are the quadratures. Every normal mode is a simple harmonic oscillator. There is an oscillation frequency associated with each of those oscillators, which represents the frequency at which that normal mode oscillates. In our problem, that frequency was equal to the phase velocity times whatever k was, where k was like some multiple of pi over L, say for the hard wall conditions. And V sub P was the square root of the Ohm's modulus mass density. That determines what the frequency is, and then each one is a harmonic oscillator, and this is the Hamiltonian associated with this. Now, importantly, let's recall in this problem, we have, so let's just summarize that. Each normal mode is a degree of freedom of the field. Each normal mode is a simple harmonic oscillator. If they're quantum, then the canonical coordinates don't commute with one another. But the coordinates associated with different degree of freedoms do commute, right? So what is the commutator of x for mode k with p with mode k prime? It's I if k equals k prime and 0 otherwise. And what about a sub k with a sub k dagger for k prime? It's 1 times delta k prime. Right. Okay. We're going to actually be on time for a change. We're going to stop there, try to absorb some of this, try to understand a little bit more what this is saying about the nature of a quantum field and the relationship of this to wave-particle duality. And then what we're going to do is think about this for not the case of a scalar field associated with vibrations of an elastic rod, but we'll think about it as vibrations of the ether, also known as the electromagnetic wave in quantum field theory of the net. All right? A great thing to end all teaching in this course, in this building, is quantizing the electromagnetic field. Nothing can be more better than that.